Hi everyone, welcome to my channel Depth First. In this video, we will be exploring the fundamentals behind dynamic programming. Dynamic programming is an algorithm that was developed by Richard Bellman in the 1950s. There is quite a fascinating story about why he chose that name. You should look it up if you are interested in learning more. Dynamic programming is a method for efficiently solving problems that exhibit two key attributes. The first is optimal substructure and the second is overlapping subproblems. We will dive deeper into these attributes later in the video, but first I'll outline what we'll cover in this video. So here is what we'll cover. We'll analyze a problem and solve it using three different methods: greedy approach, recursion, and dynamic programming. We will go over the key attributes of dynamic programming and we will try to understand the difference between dynamic programming and divide and conquer algorithms. So stick around for the entirety of this video, and with that, let's dive in. So let's say that we have 5 wine bottles that are placed on a rack. The price of these wine bottles are 2, 3, 5, 1, and 4. Each year, we are allowed to sell only one wine bottle, and that too, we can either sell it from the left or the right of the row. We cannot sell anything from the middle of the row. The profit of selling a wine bottle in the white year is equal to the price of the wine bottle times Y. So for example, in the first year, if I decide to sell the bottle from the left, the price will be 2 times 1 equal to 2, making it a total profit of 2. In the second year, if I choose to sell the bottle from the right, the price will be 4 times 2 equal to 8. And adding this to the previous profit of 2, the total profit will be 10. So in a similar manner, we need to sell the next 3 wines over the next 3 years and calculate the maximum profit. The objective now is to come up with a sequence of selling the wine bottles, whereby we can maximize the profit that can be made by selling all the wines. So if you think about it for a second, the initial instinct is to apply the greedy approach. That is to check the left and the right sides of the row and sell whatever is cheapest first. So let's apply the greedy approach and check out what that looks like. So let's start by selling the cheapest bottle first and observe the profit as we continue with each sale. So in the first year, we'll sell the leftmost bottle for a price of 2, and that makes it a total profit of 2. In the next year, we'll sell the leftmost bottle again for the price of 6. Adding this to the previous profit of 2, the total profit is 6 plus 2, which equals 8. So these are the profits for the next 3 years, and by the time we have sold all the wines, our total profit stands at 49. But now, what if I told you that there is a way to achieve an even higher profit, whereby we are not necessarily selling the cheapest bottle first? Now, watch closely for the sequence. We'll sell the leftmost bottle first, followed by the rightmost bottle, and then once more from the rightmost side. After that, we'll sell the bottle from the left and again from the left. So this sequence results in a total profit of 50, which is clearly better than 49. So what this example demonstrates that for this particular problem, a greedy approach isn't always optimal. I mean, there are a class of problems where greedy finds the optimal solution, but not this one. So instead, what we should do is explore all possible combinations. And this is where recursion comes into play, and we will explore that in the next slide. If you are enjoying this video, please consider liking, subscribing, or adding a comment. Your support really encourages me to create more content like this. I'm putting in a lot of effort into these videos, and your feedback means the world to me. Thank you. Our recursive function will explore all possible ways to sell the wine bottles. Essentially, we have 2 options. We can either sell the bottle from the left side or we can sell the bottle from the right side. So this process will naturally form a tree-like structure. And by calculating the corresponding profits for each option, we can compare them and return the maximum profit possible. So let's draw out the recursion tree. In the first year, we will sell the red bottle since it's the first bottle from the left. And our total profit is 2. So we are now left with 4 bottles, which is essentially a subset of the same problem. So given this set of 4 bottles, our goal is to maximize the profit that can be achieved. Again, we have 2 choices. We can either sell a bottle from the left or the right. If we sell the left bottle again, the profit made so far will be the price of the bottle times year plus the previous profit of 2, which totals to 8. So if a globally optimal solution can be found by combining optimal solutions to local subproblems, we say that the problem has an optimal substructure. This is one of the key attributes of dynamic programming that I had mentioned earlier. Although we are still using conventional recursion to solve this problem, this is a good point to highlight this property. Moving on, we will continue down the path of selling the leftmost bottles. You can see the profits made so far in the green labels. Eventually, we will be left with just 1 bottle and we have no other option but to sell it for a total profit of 47. Let's now compute the total profit when we sell the bottle on the right first. I have indicated the total profit of 39 in a green circle here because I plan to build the complete tree and there won't be enough space to write the entire profit calculation as I've done it on the left side. Finally, we'll sell the last bottle, resulting in a total profit of 44. So let's sell the rightmost bottle in the 3rd year. The total profit made so far is 20, and this is what the rest of the subtree will look like. Let's now sell the rightmost bottle in the 2nd year for a total profit of 10. And for this node, this is what the rest of the subtree will look like. Finally, we will sell the rightmost bottle in the 1st year. This results in a total profit of 4. And this is what the rest of the subtree will look like in this case when we either sell the bottle from the left or the right first. Now that we have the entire recursion tree in front of us, I will highly encourage you to pause the video and study it thoroughly before we review the code. The maximize profit function accepts a list of wine bottle prices as an argument. It then calls a recursive function to calculate the maximum profit, whereby it passes the start index, end index, year, and wines array as arguments. At the end, it returns the maximum profit. The calculate maximum profit function accepts 4 arguments: the start and end index of the current subset of wines array, year, and list of wine bottle prices. First, we'll check for the base case. If start is greater than end, that means we are out of wine bottles to sell, and in this case, we will return 0 as profit. Now we have 2 choices. We can either sell the bottle from the left. We'll calculate the profit as the price of this bottle times year and recursively call the function to sell the remaining bottles, incrementing the start index and the year. For our second choice, we will sell the bottle from the right. We will calculate its total profit and then recursively call the function to sell the remaining bottles. We will decrement the end index and increment the year. At the end, we will return the maximum of these 2 choices. The time complexity of this approach is O of 2 raised to the power of n, where n is the length of the wine bottle prices. This is because the function solves each subproblem multiple times, leading to an exponential number of calls. The space complexity is O of n. Let's go back to our recursion tree for a minute and observe these 2 subtrees. If you notice, or if you observe closely, you will see that these 2 subtrees are identical. So what this means in terms of the recursive call stack is that the start and end indexes of the wines array for these 2 subtrees are exactly the same. Remember when we walked through the recursion tree a few slides ago, we had already solved the subproblem on the left side before addressing it on the right side. We had already computed the profit of the left subtree and now we are recalculating it. So why spend time computing it again? What if we could save that result? This brings us to the second property of dynamic programming, where we encounter overlapping subproblems. When faced with overlapping subproblems, we can use memoization to save their results. And that's what dynamic programming is all about. Here are some more examples of identical subtrees. There are additional ones as well, and I will leave that as an exercise for you to identify. Let's now summarize the two key attributes of dynamic programming problems. The first one is the optimal substructure. So what this means is that the problem can be broken down into smaller subproblems. By solving these subproblems, we can combine their solutions to solve the larger problem. And the second one is the overlapping subproblems. While solving the main problem, you encounter subproblems that repeat. By memoizing the results of these subproblems, you can save computing resources and improve runtime efficiency. With that, let's review the code for dynamic approach. This is the recursive function that we reviewed earlier. We will add a dictionary called memo to store the results of the subproblems that we have already solved. Inside the function, we will create a key using start and end indexes. If the key is present in the memoization dictionary, we will simply return the stored result. It means we have already calculated the profit for this subproblem and we want to avoid redundant calculations. At the end, we simply return the stored result, which is the maximum profit for this subproblem. The time complexity for dynamic approach is O of n square, where n is the length of the wines array. So if you think about it, each recursive call reduces the problem size by 1, either by increasing start or by decreasing end. And the total number of subproblems to solve is the number of pairs of start and end values. Since start and end range from 0 to n-1, the time complexity is O of n square. The space complexity remains at O of n. Let's compare recursion and dynamic programming for the wine bottles problem. I conducted a test to measure the time difference between these two algorithms using a total of 30 wine bottles. The execution time for recursive approach was 9 minutes and 10 seconds, whereas for the dynamic programming approach, it was only 593 milliseconds. The recursive method handled approximately 1.07 billion subproblems, whereas the dynamic programming method dealt with just 900 subproblems. So you can clearly see that the difference in magnitude is substantial, which is why dynamic programming is such a popular algorithm, because it optimizes the solution by reducing the number of subproblems. This way, it drastically cuts down on the execution time. So this is our last topic. Let's go over the differences between divide and conquer and dynamic programming algorithms. Divide and conquer algorithms are based on finding subproblems that are substantially smaller than the original problem. For example, if you look at the merge sort algorithm, so it works by dividing the problem size in half at each step till the array is broken down into individual elements. These individual elements are then merged in a sorted order. In contrast, dynamic programming involves solving subproblems that are only slightly smaller than the original problem. For instance, let's go back to the wine bottles problem where we want to maximize the profit from selling wine bottles over time. Solving the problem for 4 bottles is not substantially smaller than solving it for 5 bottles. Another important distinction is that the efficiency of divide and conquer algorithms does not depend upon structuring the algorithm so that identical problems are solved repeatedly. On the other hand, dynamic programming is efficient only when the number of distinct subproblems is significantly smaller than the total number of subproblems. Thank you so much for watching this video. I hope you enjoyed watching it. Please do not forget to like, subscribe, and share, and I will see you in my next video. Goodbye.